So I'm going to record and it should be recording. So ultimately, when we think about computer science, what do we think about? Generally, when I used to think about computer science, I would always think about it as like, what they would show on Marvel or DC movies. They're like these nerds that they will be coding some random stuff into some random jargon within a computer, and then they'll hack the Pentagon in 5 minutes. I mean, to my surprise, that's not how computer science works. Computer science is actually much more beautiful as they portray in the movies. It's not some zero and one code that they show. And ones do play a role. It's actually the most basic form of computer science, but it's the most basic form of computer science, but it doesn't really grasp anything. It doesn't really illustrate anything. It doesn't show anything. How can someone know that this is computer science? What is actually going on? So with that being said, let's dive in deeper. So I'm going to start presenting. Let me actually share my screen. And you don't need an IDE. An IDE is an integrated developer environment, a compiler that you would put your code on. Actually, before I do that, I'm not going to be doing too much Java today. I'm just going to do a little bit of Java today. So I will be leaving in the Discord a compiler that you can download in your free time. But for now, since we're doing all the basic stuff, you can use this online compiler that I put in the link in the chat. It's just a basic Java compiler. It's kind of slow, so like give it some time, and it will work like a regular Java compiler, and will work for this lesson since we're only doing some basic stuff. Okay, so let me go here. Let me then share my screen. Okay, how do I share my screen? Okay, and desktop one, and share. Okay, so hopefully you should be able to see my screen. I'm gonna move my face in the corner, and I'm gonna start presenting. Okay, hopefully you guys can still see me, and you could see there. Okay. So, Introduction to Computer Science, February 3rd, 2021. This is a presentation I designed like I think a year ago, but it's very applicable to other computer science concepts. I made this actually initially for my computer science club that I made in high school, or that I had in high school, but it works just the same, and it will show you or introduce you to computer science. Oh, so there you go. So first and foremost, there is this common misconception that computer science is like a nerdy field. Again, like I said, it's portrayed in movies in a really weird way. Like you always see all this binary code, binary being 0 and 1. That's what bi implies. Um, and it's really just a bunch of jargon and mess that really doesn't make any sense. But in reality, computer science is actually a field of problem solving, and you do these problem solving tasks in a rather efficient way. So there's multiple ways, as you notice in our world, there's multiple ways of finding solutions to certain problems, but some solutions are just better than others, meaning that they're more efficient or they get more jobs done. And ultimately, computer science is the reasoning, it's the problem solving mentality that allows you to pursue these tasks or pursue these ambitions. It allows you to make the techniques that would help you not only problem solve to find solutions, but also find them efficiently. And you'll notice this throughout if you do pursue computer science, or if you just want to see future computer science courses online, there's a big emphasis on efficiency. So like, for example, in CS 111, which is the introduction to computer science class that is offered at Rutgers here, you learn the Java programming language, and you could find so many solutions to different problems. It's like there's so many solutions to just one basic problem, but ultimately the efficiency and the speed depend on how you develop that algorithm or how you develop the certain steps of the code. And then what's the next course that comes after CS 111? CS 1 112, CS112, which is a data structures course. And then in data structures, then you realize like what computer science actually is. You're fine. I mean, computer scientists today, or even back then, are trying to find efficient ways of storing data and being able to retrieve that data. And why do they do this? Well, if you look in like internet, or if you look at like just certain websites, right? They're charged by bandwidth. If they're using resources to access so much material, that puts a strain on the company, and that puts a strain on their like their financial capabilities. And if you look at these top companies, they know how to manage data efficiently. Now, if you look at YouTube, for example, YouTube is a really good reason of how computer science and data combined together efficiently can create something ridiculously good, something that we use today almost on a daily basis. And the reason why is because I can upload a 40 gigabyte file onto YouTube, right? It could be a 4K, 8K video. It's probably going to compress down to 4K, but that's not the point. I could upload like a 40 gigabyte video onto YouTube. And what, you know what it will do? It will compress that. It will compress that into maybe a 1 gigabyte file, or it could even compress that even smaller than that into a 100 megabyte file. And it will be able to stream it out to hundreds and thousands of people. And that is very hard to do for a company that doesn't compress that data, or doesn't take the computer science or problem solving steps to, um, manage data efficiently. So computer science at the end of the day is a field of problem solving. And really, the mentality that we have to take is, what do we need to input into our little thingy in the box over here? Sorry about that voice crack, but there's this box over here. I'm going to tell you what's inside that box later. But understand this: when you're doing something for computer science, at the end of the day, it's about getting input, or getting input from the user, input from the consumer, whatever is using your application, and then pushing some output. So we have the number 987, and you might recognize this as, well, your standard decimal system. Now, the reason why I'm mentioning the decimal system is because, well, computer science is a little bit different in terms of how data is, well, processed. Like I said before, um, like I said before, computer science, or rather computers, they use a base 2 system, meaning it's binary code, zeros and ones, and those are the only numbers that it will understand. On or off, good or bad, you get the point, right? There's only two switches, right? Two transistors, if you could say, or, well, two decisions for a transistor. But let me explain how binary works through the decimal system. So this is just your standard number. This is 987 wherever you go, right? And you've been using the base 10 system ever since you were in elementary school, assuming that, you were taught this in elementary school. But in elementary school, they probably explained to you with blocks. So the seven in this line, the seven in this line would be like seven small blocks. And then 80 would not, sorry, the eight here would not represent eight little tiny pieces. It would represent eight blocks of 10. So what is 10 times 8? That's 80. So that's what 88 represents here. It represents 80. It doesn't represent 8. And then 9 here doesn't represent 9. It represents 9 times 10 to the power of 3. Or sorry, 10 to the power of 2, because it's in the hundreds place, right? And it's in the third location from the right. So this all together becomes 987. So we have the ones place, the tens place, and the hundreds place. And what's 9 times 100? That's 900. Add that to 8 times 10. That's 980. And then add that to 7 plus 1 times 1. That's 987. That's how our base 10 system works. But how does the binary system work? Well, this is the sort of function that I have for the base 10 system. So as you can see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it will update that. Now with the base 10 system, it's a little bit different in that we have rather than having a ones place, a tens place, or a hundreds place, what we actually have we have a 2 to the power of 0 place. What is 2 to the power of 0? Well, we know that is 1. What is 2 to the power of 1? Well, that's 2. So we know that that is our two's place, you could say. And then we also have 2 to the power of 2. that is 4. So now we have a fourth place. So this is different in that rather than having 1, 10, and 100 as our base system, we now have 2 to the power of some number as our base system. In this case, base 2, or binary code, base 2 is our system. So how do we navigate through binary code? Well, it's a little bit tedious, but I feel like you guys can get it because it's relatively simple. So we have this 000, right? This is just the number 0 in decimal 10, meaning that every single location is, well, 0. So we have 2 to the power of 4, that's 0. 2 to the power of 1 times 0, that's, well, 0. And then 2 to the power of 0, that is, well, 0. But now let's see how we model the number 1. Well, we model the number 1 like this. This is our ones place, this is our twos place, and this is our fours place. So what is 1 times 1? Well, it's 1. And we continue to this pattern. So if we, let's say, forget the first twos here, what do we need to do in order to increment this value by 1? Well, we need to add a twos place. So that could be our twos place. We put the 1 there. Now, how do we model 3? Well, then we can use the previous location that we have, and now we have 3. But now we've had all the permutations or combinations that you can have with 2 different locations for binary code. So what do we do now? So now we add another position here, and this position is our fourth place. So we make this all 0 and replace that with 1. This represents the number 1, and then we restart that process all over again. So now to model the number 5, we simply change the 0 at the end to 1. And then for 6, we do that. And then for 7, we do that. And we have, well, I was about to say 7 because the 2 to the power 7 is over there. 8 of these binary code or binary values becomes a byte. So this allows us to store memory. So if you look on your hard drive, if you look on your SSD, if you have an SSD instead, or if you have a RAM, what type of unit is being used to allocate data, or what is the unit used to measure data? Well, bytes is the sort of subunits of that data. And all together, they become, well, your memory. So you have terabytes, you have gigabytes, and basically different ways of representing data. And they're all just a combination of bytes coming together. Now, when it comes to bytes, they can really represent a lot of different things, and it all depends on the context. So here, this is the ASCII code that you use for characters. As you can see, the binary code for 65, if you represent 65 in binary code, represents the capital A. Sorry about if the Discord sound came up. 66 represents capital B, and then 67 represents capital C, and then it goes all the way up to the binary value for 90, the binary code for 90, and that represents Z. And then we have different binary codes or different binary numbers for for lowercase values. For 97, it's lowercase a, and it goes all the way up to 122 modeled in binary code, and that's going to represent Z. And these are not exclusive to letters. Every single character within your keyboard has its own different or special type of binary code that allows the computer to understand that this is a certain character. So what do you guys think that this represents? Well, this actually represents hello. I know I'm just trying to rush through this, but like this actually represents a string value, and this string value is a combination of characters. So now you're starting to see how different texts are being formed. Texts are, well, what? Strings are what? They're a combination of characters. So a combination of characters makes up a string. And as you can see, each character here has its own binary value. So 72 in binary code is capital H, 101 is lowercase e. And then we continue on to that. And as you can see, the exclamation point also has its own binary code that allows it to together make the string value being text value hello. And then this is just a simple modeling of it in binary code, and that allows the computer to interpret it, what hello actually is. So this is the way that we can understand it. This is the way that the computer understands it. Now I have this yellow screen on the Zoom call or on the screen. But what's interesting is that this is actually not the color yellow. So like, I mean, you can look around, maybe something in your room is yellow. That actually is yellow. So like I have this like periodic table over there under my whiteboard. That is actually yellow because, well, we're seeing that as yellow. But I'm seeing yellow on this screen, or do I think it's yellow? It actually isn't yellow. It's a combination of red, green, and blue lights within the computer. And you might actually recognize this as RGB. That's where RGB comes from: red, green, and blue. And when red, green, and blue come together and form a combination, they can form different colors that you see on your screen. So if you zoom in on your, well, not technically zoom in, but if you get closer to your screen, then you could see different renderings of your computer screen in red, green, and blue, assuming that, you have that screen to do that. Um, so to model yellow, I have this code here: 245, 245 of green, and then 66 of blue. And each of these numbers, again, are represented in binary code. And that binary code is different depending on the context. So prior to this slide, or the last slide rather, it was representing different characters that the computer can interpret. But in this context, it's not interpreting it as a character, it's interpreting it as a different of color. So we have 245 of a color, 245 of a different color, and 65 of another color. Combine that all together in binary code, and what do you get? You get, well, this yellow thing that comes on your screen that is made up of RGB: red, green, and blue. Now, another important concept that you need to understand in computer science is the concept of abstraction. What is abstraction? Well, abstraction is being able to explain something in more simpler terms, or be able to take something that is more complex, a complex system of like commands or of directions, and make it much more simpler and much more broader. The human language is very abstract, and I mean that in the sense that we don't need to explain so much about the human language to understand what we're trying to tell the person. For example, if I tell someone, well, let's say if I tell my friend, "Yo, let's go to Rutgers today," right? Let's go to Rutgers University today, right? They'll understand that we're going to Rutgers University, right? I don't need to explain to them that they need to take this route. They need to leave their car, get into their car actually from right from the get-go, then make this turn here, 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 and then move throughout there. I mean, they can put that in a GPS, but that's not really my point. My point is saying that we don't need to tell them like every single specific direction for them to get what I'm trying to say. I could simply say, "Hey, let's go to Rutgers," and for them, that will make perfect sense. But in computer terms, it might not be that simple, actually. So what I mean by that is, I mean, normally what I would do actually in this case, I would actually, if this was in person, what I would do is I would bring out a uh, a jar of peanut butter, a couple slices of bread, a knife, and maybe even some jam. And then I'll ask my students, or ask my audience rather, to tell me the directions to make a peanut butter sandwich. And often it gets a little messy, right? And they'll miss say something that will run over the calculation. They'll be like, "Okay, open the jar, or sorry, open the, let's say, open the packet of bread," and then I'll just rip it open because they didn't give me the directions on how to open the bread. They just told me to open the bread. So I would like open it like this. And it seems kind of funny when you look at it like that. But when you look at it in terms of computer science, or in terms of what a computer can interpret it, it's a lot more different, and it kind of makes sense where the computer is coming from. So a computer needs a much more directed approach. You need to be aware that they take everything pretty literally. So abstractions help us not only divide them up into subunits, but on top of that, it allows us to organize as well. And the Java programming language is actually very abstract in relative to other programming languages. So there's actually three levels of programming languages. There's a high level language, there is a assembly language, and there is a then you got the binary language. I forgot what it's called. Um, but yeah, you have high level, which is what we'll be using, right? The Java programming language. And Java programming language is not even the most abstract programming language. I don't know if you guys use this as kids, but like there's this thing called Scratch. And in Scratch, you use some drag and drop code. And you could just drag and drop the if and else statement, or you can drag and drop something. And well, you get some sort of output. That's actually more abstract than Java, because you have literally only human words and you don't have to account for syntax. Syntax meaning how you write the code, and if this code is missing, then what do I do? But Java, in its what we're going to be using later on, is a relatively high level language. There's also assembly languages, and this is the difference between, this is sort of the middle ground between binary language and high level language. And I mean, there's less legroom in sense that there is some English words, there is an addition of English words, but you're more into, well, the computer aspect of it. Generally, assembly languages are used for, fine tuning computers or looking at the hardware side. And then binary language, as I said before, is literally zeros and ones. It'd be very hard for us to code in zeros and ones because there's no addition of English words. And with no addition of English words, we have to, well, be aware of what a computer would want to be executed with that code, or what the computer is understanding from those zeros and ones that I explained. So, what is in between input and output? Well, it's algorithms. So, as I said, we use the process of abstraction to develop algorithms, or otherwise a set of instructions that the computer can understand. And in reality, designing algorithms is a two-step process. Well, that's an abstraction all on its own. But in reality, what you would do actually is you would first write it out in English. So you would have like a piece of paper, and then you would write it out in English words. And if you write code in English words, that is actually known as pseudocode. And pseudocode is used by programmers to design algorithms before they type it out on the computer to test them out. So I would write it out saying, okay, if this works, I want this to function. Now, I don't need to know any programming language. I could just write this as a function that I want, and it will, well, allow me to process my thinking on a piece of paper. But then when it comes down to the compiler, I need to translate that pseudocode into into my programming language of use, and then test it out on the computer. So I have this sort of graph here, and I just want to show you what computer science is all about, just by a simple demonstration. So you see on this x-axis here, I have the size of the problem, meaning the size of, the input, or what do we have. And then on the y-axis of my graph, I have the time to solve it. Now, I have this, let me bring this out right here. So I have this encyclopedia here. It's a pretty big encyclopedia, right? We have different sections, and it's pretty big. But the most important thing about this is that it is in alphabetical order. So if this is in alphabetical order, that means we could do a lot of things with it in computer science. But let's start with the basics. So if I wanted to get something, or if I wanted to tell the computer to find, let's say, the word whack within this encyclopedia, well, there are different ways that it can find it. The most simple way, well, when I mean simple, I don't mean the best, I mean the simplest to understand, is you start at the first page, and then you're like, okay, page one, A, and then move on to the next word, and then the next word, and the next word, and 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 next word. And then it goes through all of this. Can't explain it. Yeah, there you go. It goes through all of this until it finds the word whack. So what is the time? I mean, this is a pretty big encyclopedia. What is the time that it would take to find the word whack? Well, it would be n time, meaning the size of the problem, or the size of the encyclopedia. And the reason why I say that is because what if it doesn't even find the word in the encyclopedia? Well, if it doesn't even find the word in the encyclopedia, what it does is that it goes through every single element in the encyclopedia to find that element. So, like, that's not really efficient. Like, why did they spend so much time trying to find something that isn't even there, right? So they spend so many time, they spend so many resources. And again, I'm saying so many resources because I'm trying to show you why computer science is necessary, or why computer science will be implemented in a problem like this. So they use this n times. So they use this approach to find it, and they could have find it, but it wasn't really efficiently done. Now, another way that you could have done this, actually, if I go back here, and is what can we do to minimize the time? Well, rather than going on every single page, what I can do is that I could just skip every single entry. Sorry, not every, skip every other entry. So I can go from A, skip a word, then go on to the next word. So let me actually go here. This is an encyclopedia of locations, so it does not have the letter A, but let me see here. So it starts off as Abrina, right? Skips a word, then it goes on to Och, then skips a word, then it goes to Och River, and it skips a word. Now that's not really, I mean, if we look at it in terms of time, it's n divided by 2, because when you're looking, I mean, the worst case scenario of it is that it looks at half the items. Now, this is more efficient than our initial algorithm, but does it actually work? No, it doesn't actually. It doesn't work because we're skipping a word after every single instance. Well, after every single one that we check, we skip a word. And what if the word that we skipped is the word that we're trying to find? And it goes through the entire encyclopedia without trying to find that word. So, although we have more, although we saved more resources through that algorithm, the algorithm doesn't work, and we wouldn't want to use that. But what is another way that we can use, another way that works and is more efficient uh, than the linear search that we use? Linear implying that we went from front to back. Well, it's called the binary search. And the binary search, what do we do? Well, we have to have a sorted, a sorted data set. So in this case, I have a sorted encyclopedia. And in that sorted encyclopedia, uh, we can use a binary search algorithm, or a binary search, to eliminate half of the book without without like worrying that we skipped the word, or skip the word that we're trying to find. So let's say if I went actually forget about it. Um, so we have letters from A to Z, right? And we can find the middle ground. So A, B, C, D, E, F, G, H, I, J, K, L, M. So M is in the middle. So we have A to M, and then we have M to Z. And we know that the word whack that we're trying to find doesn't start with an M. So does the letter W come after M or before M? It comes after M. So we can eliminate all the words between A and M. Now we've already eliminated half of our data set simply because we have a sorted sort of data set. But at the same time, we tell the computer that we make the judgment that all of these values don't work, because we know, I mean, they're not going to work, assuming that this is a sorted data set, because it wouldn't be located there. It would be located after the letter M, or after the midpoint that we're looking at. And then once it eliminates that, it makes the new alphabet, or makes the new data set from letter M, or the letter after M, N, and then goes all the way to Z, and then tries to find whack at the middle of that. And it continues until it finds the word whack, and it will eventually, assuming that, well, whack, if whack is a location, first of all, but if it doesn't, then we didn't go through every single element to go through that judgment. So in this case, the time to solve this problem is actually log n, because it keeps eliminating the data set by 1/2 every single time, because we have this sorted data set that allows us to do that. Now I have this sort of computer science code here. It's actually in Java, so you will understand this by the end of the workshop today, right? But without even knowing Java, you kind of tell like what this actually does. I mean, you won't understand that public. class thing here, and this is on its own looks kind of weird. Public static void main string r, that's really weird. Why would that be there? But you look at this location over here, it says system that out dot println hello world, and you're like, that's interesting. I see print ln. Print ln could mean print line. And we have this thing called hello world. I don't think hello world is a computer science code. And even if it was, maybe it would be declared over here or something, or there would be some type of values hello world declared before that. But um what I'm trying to tell you is that the addition of human words makes computer science in the Java programming language a little bit more easier to understand. So, in fact, this does actually print out hello world. So I have this icon here. It's the logo for Scratch. I'm going to be showing you a little bit of Scratch before we move on to the Java compiler. Let me look at the time, 9:35. Okay. So so this is Scratch. And this will allow us to, at the most abstract level, show you different concepts within computer science. Not really, I mean, not concepts, but different sort of subunits that we can use within our algorithm. So in computer science, there's a lot of things that we can use. We could use functions, we can use conditions, Boolean expressions or construct structures, loops, variables or data, and multi-threading. Don't worry about multi-threading, but I will go through every single one of these things in whether it be this workshop or the next few workshops, whatnot. But functions are basically things that the computer can uh, functions are basically something that in the computer that you execute to do a certain task. So if I want the computer to multiply two numbers, we could do that by through a function that we can develop, or the computer comes inherently. There's conditions. So conditions allow the computer to make a judgment for itself. So if this sort of context is true, then it will make that context, well, true. And if there's a certain context that it's false, then it will make that context false. What I'm trying to say here is that there is a condition. The computer can understand what context it is in, or the environment it is in. It can make a judgment for that. Boolean expressions or control structures use conditions. So like I said, conditions allow the computer to find a certain context of the context that you're currently in right now. And then Boolean expressions or control structures use those conditions to make decisions for the computer. So it's not really useful if a computer goes from line to line down, all the way down like that, because really it's not really doing anything. It's just executing a program that you run, and it's going to eventually end once you finish the program. It doesn't really have like a use. Like, what I'm trying to say is that it's if you're going to create an actual application, you wouldn't you would most likely include Boolean expressions and control structures, because what it does is that it uses the conditions that it found in the previous example, conditions, true or false value, and then pursues different paths, because you don't want the computer doing one linear path. You want it to branch out into different paths that it can pursue. There's definitely loops. This allows the computer to do a function multiple times. Variables and data is probably the most basic type that I think we're going to be doing in this video or in this session. So in variables and data, this allows us to store different values relatively with ease. And multi-threading, you don't need to know what it means. I mean, you don't need to know how it works, but all it is just running two scripts at the same time, running two algorithms at the same time. It's doing two things at the same time. So I have this example here. This is a Boolean expression, meaning that it tries to find some sort of certain context, and then it executes some certain context based on that certain context. So it says here, when flag is clicked, say hello world, and then stop this script. Again, this is just some Scratch to, give a little bit of a warm up before we go into the Java programming language. So we have this sort of Boolean expression. Boolean expression is basically any value that is either true or false. So it's technically binary. You can kind of say it's kind of like binary, but there's only two values, and those two values are true or false. And it's true when we click this sort of green arrow, but it's false when, well, we don't click this arrow. So if we don't click this arrow, it's not going to say hello world. But once we click this arrow, it will say hello world and then stop the script. Again, we're giving the computer a context to sort of study, and based on that context, make a decision. So just this 3 lines of code outputs two different lines of the program can pursue. One is printing out hello world, and the other one is not printing out hello world. Oh, now this is another control structure. This is an if and else statement, and this allows the computer to pursue multiple paths as well. So it says here, if the mouse is down, say hello, else say goodbye. So if my mouse is over here, for example, right, what is it going to output? It's going to output hello, because it says here, if mouse is down, well, my mouse is down. So that's a true statement. So since my expression is true, my Boolean expression is true, then it's going to execute hello. But if I put it up all the way over here, the mouse is not down. And since this Boolean expression, or the true and false value here, is false, it's not going to execute this hello statement. Instead, it's going to execute goodbye. And we're not confined to, if just ifs and else statements. We have an if state and then statement. This is not actually not in Java, but in Java it's just simply if, and that will execute if the value here is true. You have an if and else statement, like I said before. We have a wait until statement. This again allows the computer to just wait a certain amount of time before it executes. And then you have this. This is basically a for loop. I'm actually sorry. This is not a for loop. This is a while loop. Um, a while loop meaning that while something is true or while something exists, until it reaches that sort of false or negative, until it reaches a certain condition that we don't want it to be looping afterwards, then it will stop the code, or it will stop running the code that is within here. And we're not confined to those loops as well. So like I said in here, this is sort of like a control structure for just one decision making besides this repeat here. We also have loops. So this says repeat 10 times. This is basically a for loop at the end of the day, because a for loop meaning that it continues until it reaches 0. So it's going to be like, okay, once I execute this for loop once, I'm going to decrement this, decrementing meaning by subtract by 1, and then um, it's going to continue decrementing or decreasing by 1 until it's 0. And then when it's 0, then it's no longer going to repeat the algorithm. Forever, I mean, generally you want to avoid forever loops because, well, they're inefficient. And the only case I would think that you would use forever is if you're running an algorithm 24/7. And even if you're running an algorithm 24/7, you need it to, stop using resources eventually. So I wouldn't generally, if you use it with Java, it's going to hit you with an error saying you're using too much memory, because we are using too much memory or too much RAM within our computer. So we avoid forever loops, and in Java, it's simply inefficient programming. And we also have variables. And when you think about variables, variables are just ways that you need to store data into the computer. So that is very important, because storing data into your computer is how you're able to retrieve data from your computer, edit that data, and then do lots of cool stuff, do algorithms with that data. And there's different ways of changing that data. You can first instantiate it or create the variable, and then you set a value to it. You could change the variable type. You can change the variable altogether. You can print the variable, and you can then delete the variable. So let's code. I'm going to close out my slide, and then I'm going to open back onto my Eclipse browser, Eclipse compiler. So I provided the link in the chat for a, actually, how do I stop sharing? Okay. Okay. So I provided a link in the chat for, let me see. Let me post it here. Greg left a heartwarming comment. Okay. There you go. So this is the compiler that you can use for now. I'm going to be using Eclipse. Eclipse is probably the best browser that you, not best browser, the best IDE you can use for Java, because it gives you that integrated environment, keeps everything organized, and it even like fills in the code for you, which is really good. And I do actually most of my projects, my Java projects, on Eclipse. So if you, I'll leave a tutorial how to download Eclipse in a in the Discord. But for now, you could just use the link that I provided in the chat to test out the code. Okay. So let me do file, new. I'm gonna create a project. I don't know if you guys know, but if you guys know about GitHub, but GitHub is a way that you could store code online. This allows collaborators or code collaborators. So if you're collaborating on code, for people to share it, and then they can get that data, put some code inside that program, and then they could uh, share that data as well. So yeah, yeah, you can. I'm pretty sure. A lot of people actually create, like, just look at Among Us, for example, right? It was just an idea, right? And then it just shot up like crazy and they made hella money. Okay, I'm going to be sharing my screen again. Okay, so hopefully you guys can see my screen. I'm gonna make this a tad bit more bigger. Oh, okay, it wants me to create a project name. I'm gonna just create this as what should I name this? Let me do workshop. Actually, let me do intro CS workshop. And let me just finish. Let me don't create that. No. Okay. Don't worry about the code that I have there. That's actually the code I've been working on. I was just creating a GPA calculator. Okay. I want to see if this works because I didn't create it. I don't think I created it correctly. Anyway, let's do workshop 1. Okay, let me run this. Let's see if this runs. Okay, this is good. Okay. Okay. So I have this sort of we only got like 14 minutes, but don't worry, I'll cover some basic Java for you guys for today, so that you guys are not left empty-handed. So you have the Java compiler that you're using. Now, I don't want you guys to be worried about what it says here. Now, as you can see, it has some computer jargon or some code here that's already, that's pretty difficult for a beginner to comprehend. Reason being is that this is sort of an issue with Java. Not an issue with Java. It has a purpose, but it's a little bit difficult for it to explain to a beginner. But I'll try my best. Basically, I just want you to understand that the public class, and then the public class is where we store all our code, and it has a much better purpose when we get into things like object-oriented programming. And basically the definition of a class is a framework of a program or framework of an object. But in this case, it will serve as a medium of us putting our code. So we can put Java code within our public class, and then you can name it whatever the hell you want. I just put workshop 1 because that is reflective of the context that we're using this class in. And then we have this thing called the main method. The main method is instantiated like this. Now, I don't I don't want you to be worried about what every single element of this sort of this main method entails. If you get something like Eclipse, it will automatically import this for you, right? The main method is what the compiler is what I'm using right now, the Eclipse or the program that I'm using right now to actually write the code. It will try to find the main method and then execute that. So whatever is in within these curly brackets, it's going to first find the main method because it's named main, and then it's going to execute whatever is within these curly brackets. So in the curly brackets is where we're going to put our Java statements. And the main method is not the only method we're going to be seeing. I'm going to do a methods video a little bit later in another workshop, but for now, we'll keep main method like this. And Public is literally what it means. It means that it's accessible. You don't have to worry about string args, but just know that, well, it's necessary for the main method to have this sort of instantiation, or otherwise method signature. So if you're using the compiler that's already available that I gave you within the chat, it should have automatically come with this. So let's get some code out first. Okay, so let's do a simple print statement. So the simple print statement is system.out.println. Okay, and then I put a semicolon, and then to put what we want to print out, we put in quotation marks, hello world. Now let's break this down one by one. You don't have to worry about system.out, but just know that this is how the computer is actually accessing the thing that we want to, execute. Println is the name of our function. So println, as as I told you, is that it prints out whatever's within the parentheses. And then we also have hello world. And it's very important to put it in quotation marks, because if we don't put it in quotation marks, the computer thinks it's something that it's supposed to understand. What do I mean by that? It's going to think of one of these words. So public, class, public static, system, out, println. These are values the computer can understand because it's computer language. It's built in. It imports that from this thing called the java.lang package, meaning that it can understand that. That's what I'm trying to say. It can understand that. But if I were to remove these parentheses, it's not going to understand it. It hits me with an error because the computer doesn't recognize what a hello and what a world is. So we put it in quotation marks, and this basically tells the computer that, hey, don't worry about what's within don't worry about what's within the quotation marks. That's not computer code. It's just a bunch of characters combined. Like I said in the beginning of the video, it's just a bunch of code, just a bunch of characters combined, and it represents a string meaning text. So if I execute this, so if you're using the online compiler, then you should be able to have a execute button, and then when you press execute, it should execute hello world. I mean, first, if you're using a compiler like mine, it will first need a save, and then when you save it, please name the file name the exact same name that you have as the workshop. So the name of my file would most likely be workshop1.java, like I have over here. And it prints out hello world. And we could put multiple print statements as well. So let me do system.out.println, and let's say hello Fozon, which is my name. And let me end with a semicolon. Again, ending with a semicolon tells the Java programming language, or the Java compiler to be more accurate, that this is the end of our statement. So we tell that the end of our print statement is with this semicolon. And if we don't have that semicolon, the computer is not going to know when to stop looking. So I'm going to save that. And then when I execute it, it prints out hello world and hello Fozon, respectively, in that order. So when we have a main method such as this, it's going to go from top to bottom. It's going to go, okay, let me execute this print statement, and then let me execute this print statement. Then there are generally two print statements that you can be aware of. It's not too much of a big worry, but like if you remove the ln, what actually happens is that it puts everything on one line. So what the the ln does, you will generally use ln, not all the time, but you will generally use ln. What it does is that it prints out the word, and then it tells the compiler to just cut it from there, so no word can come after it. So if I actually put in ln here, it's going to return the same thing that we had previously, actually, because what it does is that it prints out hello world, and then it cuts off anything, so you can no longer print on this line. This line is no longer available, so when we print out hello Fozon, it's going to print out on a new line. But if I, let's say, make another print statement, not a println statement, then we're going to get that error again. So if I say hello Muhammad, for example, right, it's going to give me that error, not error, but it's going to give me that mistake over here that we generally want to avoid. And we can actually make some basic changes. So maybe if we want this on the same line, then all I need to do is just add a space here right after my name, or right after my exclamation point after my name. And well, it will make that respective change. We have that space here. And we could do this a variety of ways. We don't even have to put the exclamation point there. We could put the exclamation point here, and it will make that same change. So there's different ways of tackling the same issue with regards to that. Okay. Um, for the final part of my video, final part of this workshop rather, I'm gonna be discussing data types. So there are actually 4 data types that are the easiest to understand. I mean, they're the most basic, or maybe 5. So there's an int, there's a double, there's a boolean, there's a char, and then there's a string. Okay, so these are different data types within the Java programming language. There's actually a lot more, but these are the basic ones to get you started. So we have an integer. What is an integer? Well, it's just a number without any decimals. A double is basically an integer with double. So it's a number that you can have with decimals. Boolean, like I said during the slides, it only has 2 functions. It only has 2 values rather. It has a true value and has a false value. So you can only put true or false, and these are keywords that the Java compiler can understand. So true and false, although they sound like very English words, the programming language can understand that inherently. Char or char, or whatever you want to call it, is a character. So it's just a subset of string. It's just basically one letter, right? And then string, string is, like I said, it's just text. So you can put a bunch of text there and it will be our string. These integers, doubles, boolean, and characters, they're technically called primitive types. So these are all primitive types except the string. A string is not a primitive type. When I mean by primitive type, I mean something that the compiler has it's basically an inherent data type that the compiler has. You have to understand that strings are not technically primitive types. What are strings? Strings are just a bunch of characters combined, and that's how the computer interprets it. So that's why the string is not a primitive type. It's just a bunch of characters combined in a certain order, and that's how we execute it. So how do we create variables within Java to allow us to actually store these data types? Well, the easiest way you could do it is doing it all in one line. So you could do int, that tells the compiler that we want to create an integer. Then we name our integer. So I'm going to name it Fozon's integer to show you that you can name it whatever you want. Generally, when you're creating variable names, you will start with lowercase, and then with every word, you're going to start with a uppercase letter afterward. Don't add spaces, because if you add a space, then it doesn't register that. So make sure that it's a single space, no space. All right. The equal sign is not like the equal sign in your math class. The equal sign is an assignment operator within Java, and that allows you to assign a value to this variable name. So integer Fozon's integer can be 5. Okay, so now how do we access it? Well, let me do system.out.println, and then let's access the integer from our print statement. And again, just to keep things simple, you can, like, for example, replace Fozon's integer with X, and then replace this location with X, and it'll be the same thing. I'm just trying to show you through this identifier that you can put whatever you want as the identifier, and it'll work. But generally, when you're creating variable names, it will reflect the context of the character. It can reflect the context of the program. So when we do that, let me save it. And as you can see, it prints out the variable. So what it does, it finds the variable, because that's something that it knows. Fozon's integer is something that we created that the program can actually understand, or the computer can understand. There's a location on our compiler known as called Fozon's integer, and since it can comprehend that, it finds the location of Fozon's integer and sees what's assigned there. And we don't have to be confined to 5 with just this integer. We can change this value later on in our program. So when we create, actually, let me put this actually after the print statement. I can, let's say, put the number 7, and when I print it out, again, it's going to make that respective change. So it goes from 5 to 7 because we printed it first before we changed it, and then after we changed it, it makes that respective change. And then when we print it out, it prints out the new value. And we don't have to use int again because it already knows that this variable name is an integer. And we could do that with every single data type. So for double, you could do double, and then for double, actually, let me change this to x to make this more simpler. X, then x, and let me put x here. So rather than having an integer, we can put, let's say 5. Actually, let's do something much easier. We could do 3.14, for example, and that will work. It wouldn't work with the integer because an integer is not a decimal. It's an integer with no decimal. But double is a value that you can use with decimals. It's basically a number that you can have with decimals. And then we can change this to, let's say, 7.0, and it will make that respective change. We have 3.14 and we have 7.0 because it can be modeled like that. Now let's see what happens when I put 3 and 7. So I don't put the decimals here. So what happens? And as you can see, it actually converts it from 3 to 3.0 and then 7 to 7.0. And this is something that the Java compiler can do because we're not losing any memory when we convert from double to integer. But when we're converting from an integer to a double, we don't lose any memory. But if we're converting from a double to an integer or a decimal to an integer, that's when we lose memory because we're cutting off some decimal, and that's some memory that we can potentially use. So it wouldn't be accurate to cut off a decimal unless we explicitly tell the program to do that. But that's a whole function on its own. We have Booleans. So Boolean is kind of weird because there's only two values. There's a true value and there's a false value. And it will make that respective change because, well, that's something that the computer can understand. A Boolean X is true, X is false. And like I said, this is used for control structures. It's used so that you can make decisions, allow the computer to establish a sort of context within the compiler, and then make a respective change. So Boolean will only have true and false values. Just for the last two data types before we go, let's do a character. And to actually tell the computer that we have a character, we use a single quotation mark, and then we put the character that we want. And then when we want to change it, again, we would have that single quotation mark. And, well, we can put O. And as you can see, we have F and, well, O. And then finally, when we have string, we can't use the single quotation marks. We have to use the double quotation marks to tell the compiler that we're using a combination of strings. And then when we put the combination of strings that we want, we'll put it like this, for example, and then replace the other one with hello Fozon, for example. And when we make that respective change, we have hello world and hello Fozon. And we don't have to just stick letters into this. We can put numbers into this too. For example, I could put this, and then I could put this, and it will print it out just the same. But there's a very big difference when we do this. The big difference is that this is not a number, it's a string. The computer interprets it as a string. And the reason why this is important is because you can't just put numbers in a string and then do certain operations with it. You can only do operations with that you would use with the string. But if you want to, let's say, add a number, let's say if you want to add 1,000,000 to this number, you can't do that because it's not an integer, it's a string. So what you would need to do is convert the string to an integer, and that integer you would use to do some certain operation. But anyway, I'm going to leave it here for today. We covered an introduction to computer science. I hope that was a little bit interesting to get you a little bit hyped up of what computer science is, and to show you that it's not, at the very least, boring to what people would explain it to be, like, how it would be portrayed in movies as maybe nerdy. So I hope that I sort of try to thrash that sort of, misconception. Um, We did a little bit of Java programming. I showed you the system.out.println statement. Don't worry about the public class, public static void declaration. Generally, this will come for you. But if there's anything I want you to memorize, if there were one thing, two things for you to memorize, it would be public static void main string args, and then the system.out.println line. And like I said, we covered the data types as well: integer, double, Boolean, character, and string. And then we could do a lot of powerful applications with these values as well. But that will be for another workshop. And with that being said, I hope that you enjoyed the lesson or lecture workshop for today. And if you have any questions, you feel free to